after this, you should feel very comfortable proposing any talk you want and giving me license to define incredibly basic things and spend a bunch of time on them. So we have the time to discuss the definitions, kick them around before, other people like Yan-Yi and Rocco actually tell you what's up later on in the workshop. Okay? Okay. So this talk is actually a compressed version of a talk that you should really watch in 2 parts, given by Valiant at the Meta Complexity Bootcamp assignments, the power of distinguishing simple from random. That was in 2 parts. This is in only 1 part, so you can see it's already simplifying things. Or this talk is really a tale of 2 generators with some forbidden words. And that is not to say that I will be rude to you. It is to say that I will endeavor to avoid saying the words pseudo-random, pseudo-randomness, de-randomization, and any variations thereof. So if during the course of this talk, you catch me saying one of those words, don't throw fruit at me or beverages or anything, but do raise your hand politely and I will add your name to this whiteboard and you will get a point. Points can later be redeemed for candy or something. I don't know. I'm really figuring this out as we go along. Okay. So, key idea of this talk. Learning reduces to distinguishing simple from complex objects. I'm going to carefully work through every single word on this slide until we know what it says, starting with the word learning. So let me give a definition of learning with an asterisk, because this is going to be an extremely restricted version of a definition that'll come up in many subsequent talks. Okay? All right. So let's just get started. First, we need a target, right? If we're going to learn something, there have to be some phenomena out there in the world for us to learn. Our targets are going to be Boolean functions with n input bits. So you can see this as like 512 by 512 black and white images where the grid of pixels either represents a picture of a kitten or it does not. The function says yes when this is a picture of a kitten. The function says no when this is not a picture of a kitten. But we're not content with merely looking at concepts on fixed numbers of input bits, right? Like this is complexity theory or learning theory or something. We do asymptotics here. So we want to talk about sets of Boolean functions where we can send the number of input bits as high as we want, right? So we can talk about images of kittens at any resolution we want. So today that's 512 by 512. Tomorrow 1080p. Years from now 4K or 8K pictures of kittens, right? Either way, you're looking at a similar concept class, a set of Boolean functions built by taking the union over C sub n, where C sub n is a subset of the f of n Boolean functions for every n. So we'll identify important concept classes and they will be our targets. Any questions whatsoever about putting together concept classes? If not, next, we need some data, right, to learn from. We will have what is called an example oracle. An example oracle is a magic box with one of these target concepts inside of it. When you push the button on the box, out comes an input-output pair of the function. The input is distributed according to that curly U sub n is the uniform distribution on n bits. The input is distributed according to the uniform distribution on n bits. The function is just, the second bit is just the 1-bit evaluation on that function. This is one of the places on my slide where that asterisk, the caveat, is activated. This is actually a kind of terrible way to represent a source of data. But that's fine for us in this warm-up tutorial. We will talk about learning over the uniform distribution. This is as if we were learning to label, you know, the entire distribution of random images where you flip each pixel according to a coin toss, and then you want to pick kittens out of that distribution. That's maybe not such a good learning problem. Maybe what you care about is the distribution of images that come from cameras on people's smartphones, which I have under good authority, 30% of those are of cats. Be that as it may, I want to be super upfront and clear about where my caveats are coming from. This is one of them, deliberate simplification. It'll make the proofs easier later. Any questions about data? No. Okay. That's the example oracle. One more ingredient. We need to say what it is to successfully learn. I come from corporate America where we have something called OKRs. These are objectives and key results. So we need some objectives and key results for our learning algorithm. We want to say, okay, an alpha advantage hypothesis, like our learner is going to produce some function, right? We want that to be close in a meaningful sense to the target concept, the target Boolean function. We're just going to say that an alpha advantage hypothesis H for F satisfies that when you draw a fresh random example, just like the same distribution over examples that we're getting over here, the probability that the hypothesis agrees with the target concept is alpha better than a coin toss, just a half plus alpha. Again, this is a relaxation of some standard models, but it's definitely non-trivial, right? It's saying, you know what you're doing? You're doing better than random guessing by an alpha factor, an alpha additive factor. And you know what? That's pretty good. That's what's going to count for today. Think of your favorite way of, I don't know, scoring students doing multiple choice tests. So as long as you're beating randomized guessing, maybe you've learned something. All right.
Have a look at the person next to you.
Hey, you know,
That's something.
that's not, yeah, that's something. Maybe you've learned that you can't trust your answers to these multiple choice questions. You should desperately copy off ChatGPT or whoever's sitting next to you. Really, anything. I don't know. All right. So let's scoot all of that stuff up a little bit. These are our ingredients for learning. And finally, let's define learnability of a target concept class. Curly C, a concept class is learnable star with an asterisk if there is a polynomial time algorithm A and bounds alpha delta, those are inverse polynomial, such that for every possible number of input bits and for every possible function in, you know, the n bit input slice of the target concept class, the probability that our learning algorithm, when it has access to this example oracle, prints an alpha advantage hypothesis for F is at least delta minus 1, right? So, what?
1 minus delta?
Oh, yeah, it super is. Thank you. That's super wrong. That should be 1 minus delta. This is the kind of audience interaction I live for. So, yeah.
I'm sure he did it on purpose.
Yeah, that's in there to make sure that you're, you know what, Valentine, that's a point. All right. So probably with probability 1 minus delta, this is approximately the right thing. In other words, it has advantage over a coin toss. These bounds, I just want you to think of them as non-negligible. Like in polynomial time, we can repeat the experiment of feeding a bunch of stuff to the hypothesis that comes out and notice that it does better than a coin toss. in polynomial time, we can notice that this has like 1 minus delta, say 99% probability of actually spitting out a hypothesis with advantage over a coin toss. So that's pretty much all I want to say about the learning model for the duration of this tutorial talk. Again, more about this with all of these caveats removed from other talks later. Any questions or discussion, more errors on my slides before we move on? Okay, great. So, once again, this is our theme. Learning, which now we know what it means, is going to reduce to distinguishing simple from complex, but what are we going to learn, right? Like, what are we going to set curly C, the target concept class, to, at least for the next 60 minutes or so? We're going to measure the complexity of target concepts in terms of their Boolean circuit size. So again, because this is the first talk of the workshop, guess what? I can define circuits and you can't stop me. What is a Boolean circuit? It is a directed acyclic graph. And the nodes of that graph are going to be labeled with, quote, gates from the set and, or, not, and in for input. In is going to be x sub I for I in 1 through n to represent the values loaded at the input gates. The size is the number of gates in the circuit, and it computes naturally, right? Like you take a bit string of n bits, you shove those bits into the corresponding input gates, and then you inductively propagate the values up through the circuit. It'll help to see a picture. This is actually a pretty terrible picture for this slide because I've noticed that this is actually, I think, a Boolean formula. You'll notice that none of these nodes have more than one subsequent node.
Also, you've got words, not gate with and.
Yeah.
Wow, I have the not, yeah. Oh, yeah, wow, this is super wrong. Okay, I gotta fix this picture, both because the not gates in it are wrong, and it's not a circuit, it's a Boolean formula. But the point is, you load bits at these inputs at the bottom, you look at the topologically smallest nodes, evaluate those Boolean functions, then propagate it up until you get all the way to the output node up here, which is hopefully well-formed and not a bug like this. That's a Boolean circuit. The complexity measure is the number of gates. Okay. Let's turn this into a target concept class. So we need to take the set of n-bit Boolean functions and just slice out a chunk of it, actually a very, very little chunk with the functions that we're going to be using today, because most functions require quite huge circuit size. So size S of n is going to be the union over all, number of input bits in the naturals of f, such that f is an n-input Boolean function and f has an S of n gate Boolean circuit computing it. Okay? So that's our sequence. And just for simplicity today, because I am endeavoring to keep the number of parameters of stuff that I have to keep track of to a minimum, we're going to use, as a running example, the most natural possible target concept class, which is quintic size Boolean circuits. Just circuits. Yep. Just circuits of size n to the 5. And
For sufficiently large values of 5.
yes, for sufficiently large values of 5. So what's natural about this circuit class? Well, this is way beyond current circuit lower bound technology for explicit functions, basically. And even for related models like malformed Boolean formulas, it's nowhere near the near cubic formulas that we can prove lower bounds for. So this is just an extremely powerful Boolean circuit class that we want to think about learning. And that's going to make it, it's going to do two things for us. Number one, it's going to be a concrete value of 5 that we can just carry around instead of tracking like a particular abstract size function here. And 2, way out of reach of current technology. Okay. Any other questions or discussion about Boolean circuits?
Could you clarify why, like, it being way out of reach of current understanding is like a useful thing to?
Yeah, no, that, so, are you sure I didn't pay you to? So, the whole point of, this talk is that we can take a learning problem and reduce it to a meta complexity problem. A problem about saying yes to complex inputs and no to simple inputs or vice versa. Those problems are enormously flexible. We don't know how to solve them. We have conjectures that some of them are hard, and we have other restricted versions of those problems that are actually easy. So there's like this simple from complex phrase here is doing a huge amount of work in terms of hiding a rich landscape of meta complexity problems. So I'm picking something that is deliberately out of reach of both learning algorithms and circuit lower bound technology. So we can kind of take one of the cleanest and sort of most overpowered meta complexity problems and sort of see what it's capable of in this talk. And also kind of what it's not capable of, which is more a limitation of our own knowledge, maybe. I don't know. Does that make sense?
Yeah.
Good. Yeah, we're exercising this. So that's why a powerful class. Sort of like reducing stuff to set, right? Except instead of set, other. Okay. So we got learning, we acquired our target concept class. Now let's talk about distinguishing. I want to talk about distinguishing stuff from random. So let's say that we have a distribution G over 0, 1 to the n, so just m length bit strings. We say that an algorithm D, gamma distinguishes G from random if the following equation holds. So we've got 2 terms over here. One of them is how much the distinguisher enjoys saying yes to inputs from the generator. So what's the bias towards the distribution G, right? Probability that when we sample little g from distribution G, distinguisher says yes, minus probability when we sample y from m truly random bits that the distinguisher says yes here. So if this absolute value is large, then this means that there is some tendency or bias in the distinguisher D, which we call the distinguishing gap gamma, to say yes or no more often than not to one of these distributions. So this is our formalization of like, okay, can you tell the difference between Coke and Pepsi? I don't know. Let's feed you soda for hours and then compute your gamma. I'm sure no ethics review board would have any problems with that experiment. Okay, any questions about the formalization of the distinguishing gap? More errors, please. No? Okay, very good. Another word, reduces, right? Reduction. So we know what learning is, we know what distinguishing is, and now we need to fill this in with a reduction. And on one side of the reduction is going to be a learning problem, and on the other side of the reduction is going to be a distinguishing problem. Great. So let's talk about learning from distinguishers. The source for this is Salil Madan's take on something called Gauss lemma, which is one of the, I'm gonna have trouble with some forbidden words for a little bit now, which is one of the earliest concepts from cryptography. This part of the talk is essentially an aggressive simplification to the point where there is almost nothing left of a paper by Goldberg Cabinets, where they use other learning from distinguisher arguments in a similar way, but they use a different take on Yau's lemma that works in a much richer learning setting than the one that I just sketched. It doesn't have asterisks. Where they're going, you don't need asterisks. So I just want to say, if you want to see a truly worked out version of this argument, please read that paper or Kothari and Levini or Salil Madan's Learning from Refutation paper. So these are the sources for what we're about to go through now, where I'm about to state them. All right. So a little bit more notation. F sub curly L to the big L is the set of all Boolean functions with little l input bits and big L output bits. We call the relationship between this little l and this big L the stretch of a generator. And let's say, for reasons, we wanted to take a certain amount of input bits and stretch that to a longer amount of output bits. And the resources that we have available to us are a function, f, that we can make oracle calls to. Now, what I want you to imagine this as is as a transformation from the function f that, to begin with, it takes n input bits, right? Because that's what all our concepts do. And instead, it's going to come over here and take n times n input bits and produce n times m plus m output bits. More output bits than you started with. Thus, we would say that by transforming little f into this function dp sub mf, we have a generator of stretch plus little m over here. And this should be super reminiscent of the example oracle, right? Because if you look at the example oracle, then say you draw m examples and then feed them to the example oracle, right? Now how many extra bits of information do you have? You have m. You have the f labels of those examples. So this is the intuition that I at least have for, which is potentially wrong, something called the direct product generator. So this generator takes as input m n-bit strings. It has oracle access to f, some, n-bit function over here. And first, it just echoes out the n-bit strings that you gave. It says, okay, here are those verbatim, fine. And then to stretch the input just a little bit by n bits, it applies f to everything. You get m extra bits of information coming out. And now the next thing is super important, please ask questions if it's not clear. This is transforming just one function into a generator. Right? Look, single point over here, single point over here. What if I have a concept class, right? I want to apply this transformation in bulk to the entire concept class to get a collection of generators on the other side of the arrow. When we're going to denote that for a concept class curly C, dp sub L of little m curly C is going to be all the generators built by taking each n input f in C, okay? Yeah, right?
Mark, I'm trying to understand the intuition behind the direct product generator example. Why do you need, is there a canonical ordering or something like that that you can impose on these n, n samples essentially that you're drawing? And if so, why do you need the extra plus m term with the echo x1 through xn? Or am I sort of like misunderstanding how?
Maybe I've got the types wrong. Like each of these
Yeah.
is an n-bit string. I've got m of them.
Yeah.
So that accounts for this n times m output bits, right?
Yeah.
And then, oh, canonical ordering. You mean, what if I like mixed in my evaluations of the function into this, right? Like maybe what if I presented them as pairs, like x, like this, x sub one, f x sub one, x sub two, x f sub two, like interweaving like that? I probably,
That wouldn't change it, I don't think, but.
like that wouldn't change the number of bits on the input and the output side.
Okay. I think you answered the question, that's right, like, yeah, okay.
I think the particular ordering is not important, but how the proof is executed will depend on the order. It's I think that'll go into the details of implementing the proof. Oh, yeah. So, good. So clearly, this stretch function is a parameter of this bulk mapping, right? And the point is, it only depends on n. So every time I transform an n-bit function into a generator, I calculate how many times I'm gonna sample essentially from the number of bits in that function. Any other questions about direct product generator?
Like, what's the purpose of like, for the collection, the subscript is L n, or the individual is L of n? Like, just the very last one. BP, like, for the collection, it's the subscript is L of n.
Oh, yeah, I guess I really could have put a parameter over here, but here I was just thinking of it as probably it would be better if I put L's on both of them to make it clear that also over here I get to choose how many times I do this, right?
Is the question whether it's to come to typo, the L of n in the very last line?
Right.
Oh, yeah, that's super wrong. Thank you. Hey, yeah, what's your name?
Elon, SIHA.
See how?
Being overdid.
You didn't get the second point for correcting the circuit.
Should it just be DP sub L with a lead?
I think that's a question of being overly pedantic and explicit. That one I'm gonna keep, because that one I'm gonna say is pedantry in the slides instead of errors in the slides. But I do appreciate the concern. Okay, great. So that's the direct product generator. So Now, let's sort of scoop the definition of that up and keep around our notation. That's what it's called, fine. And now we have our statement of Yau's lemma via Verdun. So this is the motivation, by the way, for collecting together the DP generator for like our entire concept class. Is this lemma. Learning, asterisk, reduces to distinguishing in the following sense. If an efficient algorithm 1/5 distinguishes a direct product, concept class C, stretch, depending on n, L of n over here, from random, then curly C is learnable star in poly n, L of n time. So we get a time complexity that depends on the stretch of the generator in this lemma. Okay? I am not going to say much at all about how this is proved, but I am going to give you the 3 key ideas so that we can move on to understanding, like, how are we supposed to set L and Y? Okay, idea number 1, hybrid argument. So on one end of the spectrum, we have our actual data distribution, which is clearly pictures of kittens. On the other end of the spectrum, we have totally uniform random bits. So a hybrid argument says that if I can distinguish the extremal points of this distribution from each other, then there's going to be an index somewhere. This picture is not to scale. There's going to be an index somewhere where I can distinguish 2 adjacent hybrid distributions, okay? And what the actual hybrids look like is, okay, these are all uniformly random bits, right? Because we're learning over the uniform distribution. This, by the way, is where I'm making my life super easy by only learning over the uniform distribution. This is where I'm using that asterisk. Uniform random bits, no distinguishing, everything is fine. Over here, we basically generate M-ish hybrids by saying, okay, replace some prefix of these by also a distribution over random coins. There will be an index where a distinguishing gap is witnessed. It's first idea. Second idea is we believe the distinguisher, right? If you recall, the distinguishing equation, it has a preference towards one distribution or another. That preference will be maintained here at the pair of indices that witnesses the hybrid gap. So basically, you can figure out what your distinguisher likes more. And you can guess, okay, well, I think this is from the ith hybrid or the ith plus one hybrid. Check what your distinguisher says, and then answer accordingly. So this is just a believe the distinguisher argument. This shows up in many cryptography constructions. Notice that I did not say any forbidden words. And then finally, this will give you a randomized predictor, right? Because you're going to need to be able to somehow get access to the suffix to get the hybrid distribution that witnesses the gap. Well, you can use constructive averaging to sort of sample a bunch of those suffixes and run a contest to see which one is kind of good for everybody and sort of bake a final hypothesis in. So again, these are the proof ideas. I do not necessarily, I'm not going into these in any detail, but I just want to say that once the direct product generator and the hybrids are set up, you can execute the argument from like, what's that thing? Goldreich's cryptography textbook in two parts. You can basically read the entire argument for how this works by pasting together chunks of these three ideas. It's really nice.
Good question.
Yeah.
So the advantage here would be like most one row or something because VL stuff's 100.
Yeah. Thank you. So the advantage, not only the runtime, but the advantage of the weak learner is going to be governed by how we can set the stretch. So we really want to be setting that stretch as small as possible in this setting, which is just kind of weird, right? Because usually when we have generators for other reasons, we want the stretch to be as big as possible. Yeah.
Okay, it sort of makes sense, because here we want to be able to break as weak a generator as possible.
Yeah.
So we're talking about what happens if we break it, rather than what happens if it exists.
Yeah, what happens
Yeah,
if it's
for
secure? Yeah. No, this is all about the utility of breaking this generator, so we want that to be as fast and easy as possible.
That's what side you're on.
That's right. And the art of this works out to switch sides repeatedly,
Yes.
Whenever it's convenient for you.
whenever it's convenient.
Okay, this workshop is all about being mercenary with respect to meta complexity problems.
Trying to understand everything here, the previous slide, the capital L depends on the size of the complexity class C, we're using n to the fifth from large value of 5, so capital L depends on 5.
Yes, capital L is gonna depend on 5, and, how much time do I have left?
Instinct.
Well,
We
30-ish, 40-ish.
we'll probably even see exactly how capital L depends on 5. That's why 5 is 5 instead of like a parameter, because I definitely could not put a parameterized like size s to the n argument together in the time it remains. I'm bad at compression. Okay. But maybe that's because it's NP-hard. All right. So now we know almost all of these words. We know what we're shooting for. We know what we need. We just need an algorithmic problem that 1/5 distinguishes this guy, the direct product generator, where we've taken the n to the 5th size circuits and turned all of those into DP generators for some F. And we have the flexibility to set L in response to this algorithmic problem. So actually, like, we're in kind of good shape, right? We can gaze upon our zoo of meta complexity problems, find our favorite, set L in response, and then get a beautiful learning algorithm. And, you know, normally at this point in a talk, I would define the minimum circuit size problem and tell you that it's the answer to all of your hopes and dreams. But today it's not, for reasons that are deeply frustrating. So here's an apology slide. I actually don't know how to learn this complexity class if simple in our, repeated learning reduces to distinguishing simple from complex. If we take simple in that phrase to mean small circuits and thus MCSP, I can't do it. I cannot reduce this problem to MCSP. Don't know how. Here's more hybrid kittens by way of apology. So instead, what we're gonna have to do is borrow insights from Goldberg cabinets and get ourselves a different definition of simplicity. And it's still, it's still the same setup. We will set L in response to the characteristics of this algorithmic problem. But yeah, it's just, I don't know how to reduce this to MCSP. So here's the first open problem of the workshop. Fix this. Okay,
Because you're not given like the whole truth table, you're just given random examples.
it's that, and it's because of lower bounds on the circuit complexity of the multiplexer. So I might even get to that. And if I don't, ask me about circuit complexity of the multiplexer later. It's absolutely fascinating, and it is an obstacle to getting these techniques to go through for MCSP. Hopefully, we will see that. Soldier boy. All right. So now let's define simplicity. It will be complicated, I'm sorry. Specifically, we are going to use Allender's time penalized Kolmogorov complexity. So let U to the D, that's going to be a universal Turing machine that runs program description D, and maybe importantly, I'm actually not sure, it has random access to the program description D. So now we're going to define the K big T complexity of a string to be the following form. We're just going to step through this line by line. So it's kind of a local complexity, because what we're going to do is we're going to think about the complexity of the following problem. I have a string in my brain, and you have addresses into that string, and you give them to me, and I have to have some amount of reference material on the side, and I have to do some amount of material work of computational work to say, oh, okay, you asked for index I, the bit at index I is 0, or the bit at index I is 1. This just formalizes the minimum amount of reference material penalized by time that I can have to do that process. Okay, so let's step through that formally. A big T of a string X, a bit string, going to be the minimum over length of a description plus little t, ignore time for now, such that for every B in 0, 1, or star, star is going to be an end marker. For every index, at most the length of X plus 1, the universal machine running the program D, right, on input I and B accepts in T steps if and only if the ith bit of the string is actually B. So it's more like you have a bit in mind, you're like, oh, is bit J a 0? Or is bit 17 the end of the string, right? You're asking about star. Okay? So the reason that I say this is penalized is because notice that what we are minimizing is the sum over the description length and the upper bound on the amount of time it's going to take me to check each bit of the string that's coming. I don't know if there's anything else I can say about that. Any questions about K big T? Yeah.
I must have misunderstood the definition. U, D, I, B. U has access to B, and not just randomly access D and pick it, except in only.
So U has
Access to.
random access to D, and then I and B are on the input tape. So if you write a program that says, oh, on your input tape, find index I and do something with it.
That would take time, I, which would be. Go ahead, sorry.
I don't know, it's fine. The universal machine will pass through access to the values on the tape, I and B. Does that make sense?
Maybe it's, like, B is not the answer, B is like a potential answer, you're checking whether X equals B.
But if you can check, then how does you access B? I guess. is the question.
So it's a bit, so it doesn't really matter.
U is a bit on the input table.
So you doesn't have any access to X, he's trying to figure out.
Yes, U does not have any access to, thank you, good. U has no access to X. U has random access to D, a program, which we can see which is meant to be a description of X in this sense, right? So think of running the universal machine, and the program that you're running is meant to take as input index I and bit B and check, oh, at index I is the bit B.
So does it, the program has random access to access B or
The-
doesn't matter?
It might matter, it doesn't have random access to B in this set. Awesome.
Since you're like adding T to the size of D, my intuition is it really, so they're kind of equal factors. You can sort of like assume that T and D are, the T is roughly the length of D. Otherwise we should be able to like increase one and reduce the other. And so, so we have like enough time to read all the bits of D. So where random access is important isn't really like access to the input D or I or B, but to the fact that we're simulating random access to X.
Yeah, yes.
That makes sense.
So if you hard code little pieces of X in D, that you've got random access to, and that's valuable. Because if you were to do that in a circuit, you would have to pay for a multiplexer. And I can't figure out how to do that. But over here, you can hard code stuff inside D and not pay for it. So,
Why do you need star there?
I'm not sure that we absolutely need it, but it definitely makes a bunch of basic theorems about this notion easier to prove to have an end marker.
Okay, so star is your star if you're bigger than the length of.
Yes, you are.
So it's more of a blank than a star.
Yeah, it's really kind of more of a blank than a star. So it's more like anything out of range should say star. Like, oh, that's out of the index.
It's not wild card, it's.
No, I'm sorry. Yeah, it's not a wild card. Let me change that to
Blank.
blank. There. Thank you. Any other questions about K big T complexity? No? Okay. So we kind of scooted up, and let me give you some facts about it. First fact, random strings have high K big T complexity. So a while ago, maybe on the title slide, I struck out the word random and replaced it with the word complex. But if we use almost any reasonable metacomplexity problem, we're going to see that a random object requires a large description. So if I sample an X uniformly at random from n bits, and I check the probability that it requires a description that's like at least 1 in 64th of itself, that's very high. It also has universal upper bounds. This comes to memorization. This is the cost of memorization. So there exists an absolute constancy. Here I'm kind of eliding the choice of universal Turing machines. Please do not worry about that. This isn't that kind of talk. Where for every X, the K big T of X is at most the length of X plus C times log the length of X. And this is pretty much the time and description length overhead required for a program that just memorizes X inside its head, checks which bit you're looking for, and goes to the address of that bit. using its random access to its own description. And then finally, this is very similar to what Russell was observing. And this is also one of the very frustrating things about what's going on here today. K big T sandwiches circuit complexity. So let's suppose that we've got the truth table of F. And F is an n-bit Boolean function. The KT, K big T of that truth table is going to be within polyfactors of the circuit size required to compute that function. Why is that? Because you could certainly memorize the circuit that computes the function. And when you get an input, that's asking for a particular bit of the truth table, right? Run the circuit evaluation algorithm and report that back. So these are very close, and yet K big T is going to be able to be our distinguisher, and MCSP is not. All right. Oh, sorry. Any questions about the K big T facts before we use it for stuff? Any glaring errors in the K big T facts before we use it for stuff?
The other direction, is where you're saying the annoying part of simulating a multiplexer comes in, because if you want to actually like take an arbitrary algorithm that has random access to the string D, you need to be able to like look up a bit with
Yeah.
a small circuit.
Yeah. And I don't know how to do that. And we actually have lower bounds on the multiplexer function that seem good enough to block the naive approach in this setting.
That's gonna like say the polynomial factor is like bigger than Y.
Yeah, and the polynomial, so the sandwich isn't tight enough to save you from the multiplexer lower bounds, is roughly why I think we can't use MCSP here, and it's really terrible. But we sure can use K big T. So let's take a look at that direct product generator and see what we can do to it with the K big T meta complexity problem, which again is a very beefy meta complexity problem. So first, let's suppose that this F that we have transformed into the DP generator has a quintic circuit. So there exists some circuit C that computes F with at most n to the 5 gates. Now our goal is to bound K big T of Y for all Y that are like in the image of this generator. So basically, no matter which samples I feed or which input I feed to DP subbound of F, I should be able to get a K big T bound on the output of the generator, right? And let's just recall the definition of the DP generator again. It's, M and bit inputs concatenated with M evaluations of the function. Very good. Oh, no, okay. So how do we bound K big T? We make up a description and then calculate like how much computation and description length did that description take up? Here's our description. So on input, index I and bit B, what are we going to do? Index I.
Is the D going to be the circuit description for F?
It's going to be in there, yes.
Okay.
But it can't be the only thing, right? Because I could range over this whole mess of stuff, right?
Right.
So the circuit's definitely going to be in there, but we also gotta.
You gotta randomly access which XI we're talking about.
Yes. So imagine that we're writing like an assembly program where we have like store instructions or like literal data or whatever that we put into the program. That's what this stuff is. We're storing again, for random access later by the universal machine, we are memorizing these samples. How much does that cost? That's mn bits. Then we're gonna store C, right? Those are our two things. C is gonna take like big O S log S to store. That's just an encoding argument for writing down the DAG of a circuit. I'm not gonna get into that right now, but so much, how many bits it takes. And now we're actually do some work. Given the input, we're gonna say, okay, which like side of the range are you in, right? So if you're asking for an index on this side of the range, then we got that memorized. So we can just calculate and random access it out the door and, do the check, we're done. And that, the computation involved here is super simple. It's like log steps or something, linear at most. This is almost nothing compared to the amount of bits that we're paying to store these guys. So that's good. Next, okay, let's say it wasn't in that range. So where is it? It's over here. What do we have to do here? We have to evaluate a circuit. And we have to evaluate it on like X sub J for some J that we compute from the bit I. So there's like a little bit of indexing arithmetic that we have to do. It's fine. We can do that kind of arithmetic with a Turing machine, super cheap. So how expensive is this description of this string? Because remember, K big T complexity is about a single string. But what we're doing is we are getting a universal upper bound for every string in this collection, right? The image of the DP generator applied to that entire quintic circuit concept class. Okay. So for every Z in n times n, which again, we can think of as m examples. For F, we have that the K big T of the direct product generator with F evaluated on this input Z is at most n times n plus L, roughly. I'm eliding some very cheap computational factors for indexing arithmetic, and I'm evaluating I'm eliding the time bound for evaluating the circuit. But this is still very bounded. And what we want to do is we want to consider this situation, right? We want to set L of n, because remember, we get to pick m. We get to pick the number of examples. So all we got to do is, sorry, I want to say that. Okay, all we got to do is set the stretch so that there's way more of these bits than it takes to describe and evaluate the circuit. And then we're golden. We've got our distinguisher. We can activate Badon's take on Yau's lemma. We've got learning subject to consequence. Okay, so here's the formal-ish claim. We need to establish a threshold, right? Say testing if KT of, that should be a different variable, that's terrible. Testing if KT of some input is at least NM plus L distinguishes this direct product generator from random for a sufficiently large L of n. Just recall this is the distinguishing gap equation where I have, yeah, right. Here, that should be a W, sorry. Well, pretend that's a W because we're asking about the distinguisher on this. This, by our argument on the last slide, this is always gonna be zero. It's always gonna say no, right? Because it's never gonna be higher of this. We just exhibited a machine that witnesses it's always smaller. And over here, well, a counting argument tells us that one of our Kolmogorov complexity facts was that fully random strings are, have high complexity, i.e. more complexity than this, with extremely high probability, and that should be enough to get us up to the gap 1/5. So we just solve this to obtain the L of n that we should set. And that's the learning
And
algorithm.
it's just gonna be like a polynomial bigger than n to the fifth.
It's n to the 17 in my handwritten notes, but that's way
Really?
overkill.
Oh, okay.
Yeah, no, that's, and 17 is a funny number. Yeah, so that is the end of the slides portion of the talk. So are there any questions whatsoever about this extremely sketched reduction from learning with caveats to testing a K big T threshold? You know, there.
Much about the direct product behind it. There's no direct product, then, sure, that's fine.
It really is. Right? Direct product, you have like one, so direct product of a function f is to apply the same function on m different inputs. So except for like having that prefix with all the inputs, the suffix is the direct product.
Oh, okay.
So it's like you're exposing the seed, but in our case, where we work over the uniform distribution, that's actually fine, because the seed is just uniform random bits, so. So yeah, it really is the direct product of F evaluated on completely independent inputs, copied together.
I'm not sure if it's interesting, but just curious. Should this reduction extend to Hyman entropy distributions as well? Because intuitively, Hyman entropy distribution should have large PT complexity. And so you should be able to distribute between input side generated from Hyman entropy distributions versus.
Like which part do you need to have?
The XRs. Yeah, yeah.
Issue one, I think, this Yelp lemma only works with uniform distribution. So you only get the predictability if it's uniformly random. So that's issue number one. And I think this XIs, they could be, you know, they can, as long as you can efficiently sample those XIs. Like I think they don't have to be uniform, but then you need to work harder, you know, those samples with random string that have large, like more competitive, like it's, like worry that this case, let's see.
Because at least it's a Wilberton's paper about learning versus replication, it's sort of like, it doesn't, I mean, it holds true for the reduction holds true for all distributions and not just for uniform learning.
Yes. But you need a way to prepare those samples, like maybe you can get it from like the Oracle, say, or you can sample it like by yourself, but as long as there's a way to do it. I think the problem would be that maybe your predictor would start predicting the next bit of xi rather than just predicting the function values. So you can do something like. The hybrid, it's kind of a hybrid by, you know, just the last bits and. Okay, so if you just like keep the first part all the same and you have hybrids, very so. Well, I guess you're not you're distinguishing it from something, but it's not distinguishing it from random string. It's not from random string, or kind of thing, right?
Which was doing a lot of work here.
You're using like worst case testing of PT being bigger than that, right? But can you get away with some sort of average case testing?
Yeah, they absolutely do.
like read Goldberg cabinets. They even get like agnostic learning from a version of average case, MK big TP. It's really nice. It's certainly more complicated than this, but it does a lot with that, so. How much time do I have? I have 15 minutes.
This is something super obvious, but what you realize here is that this testing, if you have an algorithm to do this testing, you get this distinguishing algorithm. And what we told us before is that if you have a distinguishing algorithm that gives you learning,
Yeah.
so we're supposed to put those two pieces together in our head instead of having the algorithm for testing gives us learning. Got it, okay.
I did give you like roughly 7 words and a picture of a kitten to help you put those things together in your head.
More than that.
But yeah, no, I should probably write up like the cleanest version of this type of hybrid argument. Somewhere.
And also like, this is saying like when we have sufficiently number, when the sample size is sufficiently large, then we get to reduce to this like, testing lengths of, testing the size of Kolmogorov complex. How should we interpret it? Should we interpret it as like a hardness we're going for? Like, is it easy to test like a Kolmogorov?
No, it is not easy to test Kolmogorov complexity. In fact, there are many variants of Kolmogorov complexity and minimum circuit size problem that have been shown to be NP hard, and we will talk about that as the workshop progresses. Okay. In fact, good. Okay, I know what I want to end on from that question. Thank you. I'm going to use not all of my remaining 15 minutes to give yet another open problem besides do this but with MCSP. It's also do this but with MCSP, but with a different flavor. Okay. It is true that the big problems like MK big TP and MCSP are probably extremely hard or NP hard at the very least. Now, a problem left open by Goldberg cabinets is the following. Unfortunately, I'm sorry, I'm gonna have to skip talking about multiplexers if I'm gonna talk about this. But ask me about multiplexers later, please. Okay. So, for some context, with Russell, Lanty, and Valentine, 2016, we were able to show that learning caveats with membership queries so this is an additional caveat where instead of an example oracle, I just give you an oracle, and you can ask for whatever values of f you want. Learning to start with membership queries reduces to MCSP, the minimum circuit size. Now, this seems to be this is a similar flavor, but it uses a completely different generator. I ran out of time to cover both generators in this talk, but this uses the Nissan-Vigerson pseudorandom generator instead of the direct product generator from YAG. That's where it gets the membership queries from, but that's also where it gets its ability to use minimum circuit size problem instead of MK big TP, instead of the KT complexity. Now, what we were also able to do was define a problem AC02 MCSP is easy on average implies AC02 is learnable star with membership queries in quasi-polytone. Okay? So this is actually easy on average. That comes from the Razborov-Rudich natural proofs paper. Razborov-Rudich 97, where they were concerned with establishing barriers to improving circuit lower bounds by saying that, okay, you know, if you prove a circuit lower bound against certain complexity class with certain family of techniques, which is basically all the techniques we know how to do, you break pseudo-random functions in that class. Since we believe in pseudo-random functions, those proof techniques can't exist, but they also gave us actual algorithms for variants of meta-complexity problems. Admittedly, those algorithms don't necessarily run in quasi-polynomial time. So like we're really stacking up the asterisks on this learnability problem over here. We've got membership queries now and also runs in quasi-polynomial time, but it was progress on the expressivity of the Boolean concept classes that we can learn at all. Okay. So one might hope, I might hope, that you could take exactly the proof that we just went through and obtain the following. If AC02 MK big TP is easy on average, then AC02 is learnable. And I'm ignoring the time complexity here because I'm just talking about the existence of a reduction. Oh, we can let the time complexity be sad later. Point is, this would be great because then it would give us a better understanding of the problem of learning AC0 mod 2, which is very important circuit complexity class, from random examples instead of from membership queries. Yeah.
Is the open problem the implication, or is the implication known and the open problem is to get the premise?
It's both. It's both. Because I don't even know how to say this. This
Oh, this hasn't been formalized?
This has not been formalized. To my knowledge, and I did ask Eric Allender several times. It's very annoying. To my knowledge, there is no flavor of MK big TP that corresponds to constant depth circuits the same way that MK big TP corresponds to general Boolean circuits. And we would need at least this to even get started applying these techniques to learn AC0 with parity gates from the Kolmogorov device. So we're not just we're missing the upper bound, we're missing the implication because something might break in the proof with respect to multiplexers, I don't know, and we're even missing the definition of this problem. So it seems pretty grim, but we do have all week.
Yeah. Some of us have more than like a month.
And some of us have as much time as a whole month. So who knows? And yeah, with that, I will wrap up. So thank you so much for your.
This is not at all well formed. Can you kind of talk again about how we don't have like a reasonable idea of what the thing in the cigar shaped block would be? Like you would say, maybe say all the words you said again.
Yeah, no, I can actually say even more in different words. So Eric Allender was able to define something called K capital F that corresponds to formula size complexity by, instead of the, you know what, I'm gonna go all the way back to, wait a minute. I just want to actually have this to point at, oh. So Eric was actually able to define a notion called K capital F that corresponds to formula complexity by taking this universal Turing machine to be a universal alternating machine that runs in small parallel time. And that does have the correct relationship to, you know, NC that we would want for AC0 over here. So it's not that it is impossible to look at circuit complexity classes that are inside general poly-size circuits. There's also one for branching programs, right? And get Kolmogorov complexity style definitions for these classes by looking at their accompanying machine models and just like fussing with the universal machine in this definition and messing with how you keep track of stuff and penalize stuff in here. It's perfectly feasible. It's just that no one's done it for AC0 and friends yet because it seems horrible and difficult to do. And the reason that I'm not here talking about learnability of NC by reduction to K capital F is because I guess I've bought into the hype and believe in cryptography. So this would not be as interesting a statement for me because I would conjecture that the KF problem is probably very hard. So a reduction that says, you know, if you can solve KF on average, you can learn everything in NC, that seems a bit unrealistic to me. Whereas if you had a statement like this, if you had the right notion for MK big TP, I would say, okay, get to work trying to make an algorithm for AC0 MK big TP if you could define it. That seems plausible.
Great learning parity with noise, right?
Oh yeah, but not necessarily. Not necessarily, because this is one of the reasons that I've done this presentation based on Salil's paper instead of Kothari and Levini. Kothari and Levini use a version of Yao's lemma that automatically gives you agnostic learning. So yes, if we were pursuing that, like if we were pursuing that proof technique, you might automatically break learning parity with noise. But if instead you can sort of find an actual difference between Salil's realizable, like Yao's lemma gives you learning, and Kothari and Levini's agnostic, Yao's lemma gives you learning. If you can find a real difference there, you're not in danger of breaking learning parity with noise because you would just be learning AC0 parity without noise. But that being said, I am not familiar enough with the literature on the LPN conjecture to know if there's like, maybe there's super good worst case to average case reductions for it, that even if you get learning in just the realizable case, you automatically have it in the noisy case. I don't know.
In realizable cases, you can learn, it just goes to elimination. But no noise, learning parity without noise. So that's not a hard problem.
But that's not AC zero mod two circuits, that's just a linear function, right? So. Oh, yeah, so actually then that's fine. So then there's not an amazing worst case to average space reduction that I don't know about, because the normal problem is just Gaussian elimination. If, of course, that embeds into AC zero parity. So I guess what we might be worried about is that maybe by adding depth to the realizable learning problem, you activate some kind of period reduction. I don't know if that's a thing.
Okay. Like stupid question, why wouldn't AC02 MCSP break the LPN? Like, why wouldn't like the learning algorithm or the AC02 MCSP, yes, is easy on average. Why that doesn't break learning with parity?
Because it needs membership queries.
Learning parity is easier to do motion queries.
Yeah, so there's no contradiction, no problem. And I've been informed by a beautiful handwritten sign that my time is up. So, but yeah, but that's why. It's because to learn it all, we need membership queries. LPN with membership queries is easy, so no contradiction, no problems. Thank you again, everybody.
We have a lunch break till 2 p.m. and maybe Dari will tell us where to go for lunch because we're on our own.
Oh, yeah.
Or anybody local.